computer? Okay, we're recording. Welcome everybody to seminar 2 of the series on the Transverse Field Ising Model. I want to start with a sort of recap of where we got to in seminar 1, and then we'll quickly sort of move on. So we defined the transverse field Ising Hamiltonian as this thing in terms of spin operators sigma minus sigma plus, which are defined as like sigma plus acting on a down is an up and vice versa for sigma minus. And then we introduced the Jordan-Wigner transformation that turned those sigmas into anti-commuting fermions. So the full details of all those definitions are available on the website, which this is a screenshot from. It's very nicely formatted. Then where we got to at the very end was imposing periodic boundary conditions, which was essentially saying that HPBC is HOBC plus this extra missing term that connected sigma capital L to sigma 1. So sort of the missing term from this part. But then when we saw that when we turned into fermions, we got this extra negative 1 to the n hat plus 1. So that's an issue, right? Because eventually what we're going to want to do is Fourier transform. But in order to Fourier transform, we would kind of need to make a statement about what CL plus 1 is in terms of C1. So there's a way to deal with that, and that is to sort of split the Hamiltonian into even and odd sectors. So n hat is the sum of all of the number operators. And you'll notice that although commutator of n hat with h is not equal to 0, when I write h here, I mean HPBC. So commutator of n hat with h is not 0 because we've got these double creation and double annihilation operators. But you'll notice that we either create and destroy. Sorry, there's not meant to be a plus there. We either create and destroy, or we double create. So in other words, the number of fermions is conserved modulo 2. So that commutator is actually 0. So that suggests we can do the following. So I'll define f to the n to mean the Fock space of n fermions, and this is a 2 to the n dimensional Hilbert space, which is just a sort of convenient rewriting of the spin Hilbert space. So yeah, f to the n. So this superscript n just refers to the dimensionality, like the number of fermions. So I know that HPBC, the original thing we had, takes us from f to the n to f to the n. But we can also define projection operators that commute, where these pi p's project onto either the n even or the n odd subspaces of f to the n. So like I might want to write f to the n as f n minus 1 even direct sum f n minus 1 odd. So the fact that this commutator is 0 implies that the following diagram commutes. I.e., we can deal with the full Hamiltonian by just dealing with the Hamiltonian within the even and odd sectors. Or another way of saying that is that, like, by adding in this restriction operator commute, the fact that this n hat operator commutes with the Hamiltonian means that restriction operator commutes with the Hamiltonian. So like explicitly pi p would be negative to the n hat minus 1 over 2, which would, sorry, so that would project onto, if n hat's even, you get 0, so that's pi odd. And pi even has a plus there. So that suggests a sort of a mode of attack, if you like, which is that we're going to actually define an auxiliary Hamiltonian that acts like HPBC when restricted to the even or odd subspaces. So yeah, formally this is quite complicated, but in practice it's actually quite simple. And these things get a special name. They're called like curly HP. That was meant to be straight HPPS, PBC is restricted to P. So curly HP. And what these are is Hamiltonians that act on the full Fock space, but restrict to be the same as HPBC. But in general, curly HP is not the same as curly H like odd. So sorry, I'm gonna be saying P equals 0 or 1, which means even or odd, respectively. So curly H1 is not the same thing as curly H0. So what do these look like? Well, I mean, if you go back to the original Hamiltonian, it's actually quite natural. We're going to define H odd. So n hat plus 1 is always even. So odd is going to be equal to H OBC minus J to C dagger L C1 plus C dagger L C dagger 1 plus HC. And H even is going to be pretty much, hey, there's no mind for now. H1 is going to be that, but with a plus. So in other words, the sort of syntactically useful way to unify these two descriptions is to define like C L plus 1, because ultimately we're going to want to like extend this sum to run over J equals 1 to L to totally L rather than L minus 1, is to define CL plus 1 is like plus or minus C1, where it gets a plus for, I'm just going to write it out explicitly because plus or minus is hard. So H1 is that, which suggests that a natural definition is CL plus 1 equals C1. And this gets the plus sign suggesting that CL plus 1 equals negative C1. And using those definitions, we can sort of unify what H0 and 1 are. Or rather HP is, which is negative J sum J equals 1 to L, big bracket, Cj dagger Cj plus 1 plus kappa Cj dagger Cj plus 1 dagger plus Hermitian conjugate plus H into Cj dagger Cj minus 1. Yeah, where now this like CL plus 1 is defined like it was here. So in essence, what we've done is sort of restore the translational symmetry of the Hamiltonian in some sense. I like topologically now, this is a ring that with except it has a weird sort of twist in the case of like an even number of particles. That's all fine, because still at least the sites are symmetric with respect to sort of a site-wise translation by one, which suggests that the Fourier transform will help us to diagonalize it. Yeah, just a reminder of like where we want to get to. We want to be able to write the Hamiltonian as a sum of like modes. For some sort of operators, sorry, even more abstractly, we want to eventually be able to write the Hamiltonian like this, where these A hat Qs are some kind of positive definite operator, so that we can say the vacuum is where all of these operators are zero, and any of these correspond to different excitations above the vacuum. So we're definitely not there yet because we've still got mixtures of different operators and everything. So the game plan here is to sort of try and disentangle everything. Yeah, so we define CK to be e to the minus I phi over square root L sum j equals 1 to L e to the minus I kj Cj. And k in this case is for now just a real number that's been left unspecified. Now for this to actually be useful, we need two things from this transformation. First of all, we need it to be invertible. Which implies that there are exactly L CKs, or rather there are L CK dagger pairs. Because if we have too many, then like the Hilbert space spanned by the set of all like CKs acting on the vacuum would have too large of a dimensionality. If we have any fewer than L, it has too small of a dimensionality. So there must be L CKs if there's even a hope of it being invertible. And we also need the sort of delta function identity, i.e. like e to the I phi over square root L yeah, we need like we want to be able to get Cj by doing this sum, i.e. that like the inverse Fourier transform. And you can show by direct substitution of the definition. Oh yeah, sorry, I should kind of explain myself here. I've introduced like e to the minus I phi as like an arbitrary phase. That doesn't really change anything, but the point of introducing it is to eventually show that it doesn't affect the physics of the system. But in general, you can introduce an arbitrary rotation on every site that doesn't affect the physics. Yeah, so like the delta function identity that we need, when you sort of substitute this into that and work it through, is that 1 on L sum k element of k e to the ik into j minus j prime is a delta function, i.e. like a Kronecker delta. So sorry, I might briefly pause to kind of justify this form and sort of explain all the symbols used. So that subscript there, like script k, is some set of capital L Ks. We don't know what they are yet, but it's just some set of capital of L fold Ks. And yeah, I suppose if I were doing this completely honestly, I would just leave these coefficients completely general, like some AKs or something, and eventually work my way back. But in my case, I'm kind of future citing and saying, hey, this works as a unitary transformation on phase space. So sorry, I've written this as like defining new operators in terms of old operators, which is a perfectly good way to define everything. But what's sort of happening under the hood, so to say, is that we're taking like one basis, the set of like C dagger J's acting on the vacuum, and transforming to a different basis, which is the C dagger K's acting on vacuum. And we're doing so in a way that is unitary. Yeah, so sorry. Yeah, I guess that's the way to explain what's happening. We want to find a unitary transform on the state space. I claim I basically pulled this out of the blue because I happen to know that it works because someone else told me that it works a few years ago. And now I'm sort of demonstrating that it's unitary because this transformation is the dagger of this transformation. Yeah, and you can show, and so basically the condition that like this transformation is unitary is equivalent to saying this sum is a delta function. Now I'm going to set an exercise. These are all listed on the website, and that is to show that this thing is satisfied if k equals 2 pi n over L plus k naught, where n equals 0 to L minus 1 for any k naught. I suspect this is actually an if and only if, but we don't really, which you can show if you want, but it's not really necessary for the argument to go through. So yeah, this is like a sufficient condition to have a unitary transformation. So that kind of suggests that a natural way of choosing, so because k naught is sort of unspecified, it's kind of arbitrary up to a factor of 2 pi over L. There is a conventional choice for how to choose these k's, and that is to say go between like negative pi and positive pi, not including negative pi for concreteness. And however k naught was chosen, we just sort of line them up from negative pi to pi. Now, of course, topologically, this is kind of, it's natural to think of this as embedded into the circle, which is where the choice of negative pi to pi comes from. Yeah, continuing onwards. So let's think more carefully about the boundary conditions. So remembering that CL plus 1 equals plus or minus C1, where plus if odd and minus if even. I'll just keep it with plus or minus for now. That actually implies using that Fourier transform, or rather the inverse Fourier transform, you get that e to the I phi on root L sum over k of e to the I k L plus 1 ck equals e to the I phi over root L e to the I k ck. And by orthogonality arguments, you can show that that is equivalent to e to the ikl. Oh, whoops, I forgot the plus or minus. That's very important. E equals plus or minus 1. So in the plus or odd sector case, we have e to the ikl equals 1. So it's natural to say k equals like 2 pi n on L, like k naught is 0, mod 2 pi. And yeah, with the conventional choice, that gets us from like negative pi over L minus 1 all the way to pi over L minus 1, and also including the points k equals 0 and k equals pi. Sorry, I think I may have messed up. 2 pi into L minus 1 over L and negative of that. And for negative, so the even case, you get e to the ikl equals negative 1, which is equivalent to k is 2 pi n on L plus pi on 2. Sorry, pi on L. So in other words, we're going from like negative 2 pi yeah, sorry, I'll write it slightly differently. So in other words, like k even in the even sector is the set of plus or minus pi on, plus or minus pi on L plus 2 pi n on L, given n equals 1, 2, up to L on 2. And K1 is the set of like 0, pi, and plus or minus 2 pi n on L, given n is 1, 2, up to L on 2 minus 1. And sort of by inspection, you can see that both of these end up with exactly like L k states. So we're still keeping the dimensionality correct. So I'm going to use two results without proof. Again, these are typed up into exercises on the website. The first is that regardless of which k you choose, sum j equals 1 to capital L of Cj dagger Cj plus 1 is sum over k element of the relevant k e to the ik c dagger k ck, and sum j equals 1 to L of the double dagger double creation operator is e to the 2I phi sum over all the k's of e to the ik c dagger, where the second one has got a minus k. Remember, this is that order is very important because yeah, these things anti-commute, and so that's like negative e to the 2I phi c dagger minus k c dagger k, which is a bit, so you can see by sort of reflecting k, like substituting k with minus k, you get back to the original thing. It's just important to, yeah, keep the minus signs in order, which is admittedly annoying. So using those two results, the dreaded words, it can be shown that HP, remember, so this is valid for both the odd and even case, is minus J sum of K element of KP, e to the IK C dagger K CK plus e to the minus IK C dagger K CK plus kappa e to the I phi e to the IK C dagger K C dagger. That is a plus. Plus the Hermitian conjugate, e to the minus 2I phi, e to the minus IK, C dagger. Sorry. C minus K, C K, where the Hermitian conjugates swap the order of those two. Oh yeah, then plus H. Oh no, it's frozen. Plus H into 2 C dagger K, CK minus 1. So we are actually in a pretty good space right now, because before we had like mixtures of J plus 1s and J's. Now everything seems to be subscripted by K. Well, almost everything. We've actually got a mixture of K's and minus K's. So yeah, if you've seen condensed matter before, you'll know that this is actually, the transverse field Ising model is now starting to look increasingly like a superconductor, where we've got pairs of creation and pairs of annihilation operators that sort of look like, yeah, taking like a quasi-particle with momentum K and a quasi-particle with momentum minus K and removing both of them from the system and sort of creating an extra bosonic excitation, which in a superconductor is a Cooper pair. That's not really the case here, because there's no, there's nothing's actually been created. This is just like a mathematical trick. At the end of the day, they are still spins that are just rotating. But still, it's like a fun crossover episode, I think. So yeah, to sort of deal with the index wrangling, I'm going to have to define like K plus, which is a set of K and KP that are positive. And so sparing you the gory details, what you end up with yeah, I'll explain that in a second, where HK is 2J big bracket H over J minus cos K C dagger K CK minus C minus K C minus K dagger. Minus I kappa sine K into e to the minus 2I phi. Sorry, that's my plus. E to the 2I phi C dagger K, C dagger minus K minus e to the minus 2I phi C minus K CK. I'll thicken that up slightly. Yeah. So a few subtleties that are involved that you have to know. And sorry, the reason that I have separated these two things out is because 0 and pi have like indeterminate sign, or rather like they get missed by this k greater than 0 specification. So in the case of like an odd number of k space points, you have to include those explicitly. Just this is just sort of index wrangling. It's not nothing fancy. Sorry, I neglected to say something kind of important, which is you notice that I included L over 2 here. So I've actually assumed that L is even. The reason I did that is that the odd case is like even more annoying to deal with index wise. And actually it does actually make a difference, believe it or not, to the spectrum when we get to like looking at open boundary conditions. But yeah, in the interest of time, I'm not going to go through the odd case in detail because it's the same, really. So like, but what I can do is write up sort of a summary table of what you end up with, because this HK is a universal kind of definition. So depending on so I'll shrink it down because I've made my writing's gone huge again. Yeah. So in the case of in the even sector, so yeah, on one axis we have the even sector and the odd sector. And on this axis we have like the evenness or the oddness of the chain. So if we're even, then you end up with H0 equals some K0 plus HK, that's it. In the odd sector, you have an extra term plus H pi. In the odd even sector, you have plus H0 plus H pi. And in the odd sector, you have plus H0. And yeah, if you've got, so yeah, in short, like viewing K is, you can kind of imagine this if you think of K as like a circle, like K space as a circle. So like if you like the evenness or the oddness decides what happens at K equals 0. Sorry, whether we're in the even or the odd sector decides whether or not we get an H0, and whether or not we're in the, yeah, have an even or an odd number of points decides whether this point directly opposite K equals 0 looks the same or looks the opposite, gets included or not, in short. Cool, but yeah, so that's honestly not that interesting. What's kind of more fun is to look at to think a bit harder about what this HK is actually doing, right? Because we've just been sort of shuffling operators so far, but we haven't really thought about how this acts on the Hilbert space. So you can actually think about, so we have sort of 4 bases within like a given HK acts on like 4 basis vectors. The vacuum, everyone's favorite. The state with 1 K particle. The state with 1 minus K particle. And C dagger. And the state with 1 K and 1 in minus K. So in other words, each HK acts on like a 4D space, a 4D Fock space. So going back to dimensionality, we decided earlier, like in all of these cases, right, at least in the even case, K0 plus had exactly half, includes exactly half of the points in the Brillouin zone. So we have like LHKs, or rather L on 2 HKs, 4 to the L on 2 is 2 to the L, which is right. And you can see with a little bit of massaging to deal with the edge cases that all of these are L dimensional operators. Yeah, so HK acting on the 4D space with respect to this basis, you can actually write down the matrix representation, which is a bit of fun, which is H over J minus cos K minus H over J plus cos K minus I kappa e to the minus 2I phi sine K and I kappa e to the 2I phi sine K. Sorry, I think I'm cooked the minuses. And actually, all of these are 0. Oh, sorry, I've written the bases in the wrong order. Yeah. So in other words, this term couples the vacuum to itself, and this term couples the double excited state to itself. Whereas these sort of weird off diagonal terms are mixtures of vacuum and double creation operator. Whereas, yeah, all of these other terms are 0. The reason being, like, these things here change the number of fermions in the system, but we previously ascertained that like the number of fermions is conserved modulo 2. So these two sectors here have to be 0 because they violate fermion parity. Whereas this, but this sector down here, that would correspond to something like C dagger K, C minus K. Like we annihilate, we get rid of a fermion traveling right and create another one traveling left. So like the overall momentum change here is like 2K. So this is forbidden by momentum conservation. It's a sort of weird thing about condensed matter, right? Because we've sort of just come up with random operators on some Hilbert space, but because of the fact that they still obey all of the right, tick all of the right boxes to count as fermions, they still obey all of the familiar results about them, like momentum conservation, conservation of energy, asterisk. All these sorts of results from field theory seem to just appear in condensed matter theory, even though we've discretized everything and done sort of gross violence to the system. It's kind of a beautiful result. Yeah. So yeah, now we need to. So we're almost diagonal, like we're kind of block diagonal. But now we need to take linear combinations of 0 and C dagger K, C dagger minus K, 0, in order to turn this matrix into a diagonal matrix. So lemma, because we're short on time, I unfortunately cannot prove it, but fortunately for you, it is typed up on the website. Yeah, the lemma is that unitary matrices preserve commutators. I.e., at least for bosons and fermions. And that is that if you have, like, let's say F flavors of bosons, B flavors of either bosons or fermions, like B1, B2, B3, and so on, and you have commutator of Bi, Bj, or rather commutator or anti-commutator for plus or minus is delta ij. Then if U unitary, then you have some matrix U, F by F of C. Yeah, you have some matrix U, and define new variables. Ai is Ui, J, Bj. Then commutator of Ai, Aj plus or minus, like commutator or anti-commutator of Ai, Aj is delta Ij, if and only if U unitary. That's lemma 1. Lemma 2 is a bit spicier. If you define a spinor psi k is ck1 ... ckf, c dagger minus k1, c dagger minus kf, then first of all, commutator of psi k prime star equals, alpha beta equals delta kk prime 1 1 1 1 plus minus 1 plus minus 1 plus minus 1, if and only if the CKs are bosons fermion, like the CKs obey canonical commutators, i.e. commutator CK alpha, CK prime beta, dagger is plus minus is delta KK prime delta alpha beta. And sort of a corollary of that is if you have for fermions, unitary matrices acting on the side Ks preserve fermion character, by which I mean the commutators. If U unitary. So yeah, you can probably kind of see how this follows from lemma 1, because yeah, the condition is exactly the same. Like for fermions, these are all pluses, and this just becomes a big identity matrix. It's slightly more annoying for bosons because they're not unitary anymore, they're skew unitary, but we're dealing with fermions, so I won't mention it again. So in other words, we have, going back to if you kind of stare at the form of HK, I'll get a copy of it. I need some space. If you have, if you look at the form of HK and stare at it for long enough, you can actually convince yourself that you can re-express it as 2j times phi k dagger h over j minus cos k minus h over j plus cos k minus I kappa e to the minus 2I phi. Sorry about the signs. Where phi k is ck c minus k dagger. So hang on. We want to like find a new set of fermions that makes HK diagonal. But they have to stay fermions. But we know that if we like act some unitary matrix on phi k on this, whatever you get at the end will still be a fermion. So in other words, we need to find two unitary matrices that like when sandwiching this matrix makes it diagonal. But hang on, this is a Hermitian matrix. That's just ordinary diagonalization. Fantastic. We don't have to think hard about how to diagonalize anything.
Hey, Alaric, just confirming, you're using phi subscript k is different from phi.
Oh yeah. Right. Oh yeah, that's quite bad. That's a bit egregious. Yes, sorry. Yeah. So in other words, we need to find, so if we let like so we know, so from if we find like the two eigenvectors of this and put them in columns like v plus v minus, then we know that and call that u. I'm gonna like abuse notation a bit and just refer to this matrix as HK. Then HK u dagger is diagonal. But, and it's also like the original thing is also equal to that. The other thing I want to remark about this H matrix is that it's traceless, and so the two eigenvalues are going to be plus or minus the same number. So if you like define like new fermions, fk f minus k dagger equals uk dagger psi k, then this thing will end up looking like, yeah, fk dagger f minus k ek minus ek fk f dagger minus k, which is, sorry, I forgot the factor of 2j, which is 2j into f dagger k fk plus f dagger minus k f minus k minus 1, where this minus 1 came from using an anti-commutator on what you get from this times ek. So in other words, the whole Hamiltonian is going to be a sum over all of the k values, where I no longer need to worry about the plus or minus stuff of 2j ek fk dagger fk minus some constant ground state energy that you get from these minus ones. So I want, I do briefly want to make a point here, which is to say that we've actually found something called a Bogolyubov. Sorry, I don't want to get the attribution of this wrong, but we've found essentially an unstable ground state. So when we diagonalized the Hamiltonian, we ended up with this thing. but it had both double annihilation and double creation operators, which suggested that the vacuum that we acted on earlier, like the fermion vacuum, was not actually the vacuum. And the reason I say that is that there are like linear combinations of operators that can act on this thing to lower the energy. So the definition of the vacuum is the state on which you can no longer, the state of lowest energy. So the fact that there exists like this -1 in the end, because like these F dagger Fs are all positive definite, we don't care about them, but this -1 is very not positive definite. It means that like the system with none of the original C fermions in it actually was an excited state of the system. The true ground state, you actually have to construct explicitly. And it actually has to do with the eigenvectors of this Hamiltonian matrix. So like explicitly the psi k is UK fk f minus k dagger. So I mean, like cutting out the details, gamma k is like, you can rewrite it as like two complex numbers plus vk star c minus k dagger. Sorry, fk. And another way of writing the vacuum would be phi is like the product over all of these new F operators of trying to annihilate the original non-vacuum vacuum. So whatever state we're left at once we're done with this is the true vacuum, because clearly acting any of the FKs on this thing will end up with an FK squared, which is 0 because they're fermions. Yeah, so like in principle, so these UKs and VKs are determined by the eigenvectors of HK. And that's about as much as you can say. Sorry, the final thing I do want to mention is that, yeah, the eigenvectors are somewhat tedious to get, but the eigenvalues are very obvious. Just by doing sort of standard diagonalization arguments, you can find that EK is plus or minus square root H over J. Sorry, the way I've defined it, EK is always positive, H over J minus cos K squared plus kappa squared sine squared K. And in fact, you can actually rewrite this HK in a clever form. H over J minus cos K tau Z plus minus kappa e to the I phi. Oh no. Sorry. Yeah, sorry, by taking real and imaginary parts of like these things, minus e sine 2 phi sine k tau x minus e sine 2 phi, sorry, cos 2 phi sine k tau y. There may be a wrong minus sign there. You can actually sort of reinterpret it in a bizarre way as like b dot tau, where these taus are all Pauli matrices. Like you can sort of think about HK, there's H's and K's as an effective magnetic field acting on an effective dipole moment. And the reason I wanted to get to that is because that's where topology finally enters the game. So it'll take probably about 10 minutes to discuss that. Would you be happy to stick around for that long, or do you have to go?
Yeah, that's cozy on my end.
Sure.
Yeah, no, I'll yeah, okay. So real quickly, if you imagine like so remember phi was sort of, sorry, keeping phi totally general, right? Well, the situation we have is that we have like k, which is isomorph. So we're going to take the large n limit. So I'm going to let n go to infinity. So then we have this script k thing, which is isomorphic to z, which is included into by, which is sort of a subset of the circle modulo n's. And we have like this hk defined on discretely many k into GL of this 4D local k Fock space. However, we can actually analytically continue k, not uniquely probably, but you can find a continuous function that goes from this k space also to GL F4. So if you think about this thing on the right, we can actually regard like, if you imagine like taking a single eigenvector at a particular value of k and following it as you transport it around the k-space circle, what we actually kind of have is a U1 bundle where it's like, yeah, there's some manifold, which I'll call E, that is locally isomorphic. We have E with some projection operator that takes you to the circle, which like takes some like phase and k and just gives you the k space point that you evaluated it at. This is a different pi, apologies. And if you have some local neighborhood of like k's and theta k's, that's locally isomorphic to U, which is a subset of the circle, cross U1. So it's like we've taken the circle and like glued a copy of U1 to every point on the circle, where the physical interpretation of that U1 is the phase of the state of the eigenvector. So, I mean, in some sense, we actually have a U1 squared bundle because there are two eigenvectors that both have independent phases. So as long as those two eigenvalues never overlap, those eigenvectors remain totally decoupled. So they have totally decoupled phases. The idea of like where topology enters the game, right, is that it's a U1 bundle, but it's not necessarily the trivial U1 bundle. So as you transport the state vector around the circle, when you get back, you know that you have to agree with the original phase, but you can definitely do like a sort of, if you think about this as like looking kind of like a subset of the torus, as you transport it around, you can get a non-trivial twist in the phase. So this, sorry, that is the worst drawing ever done. So that, yeah, like when I say a trivial U1 bundle, that is like transporting the state and not introducing any phase at all. Whereas a non-trivial state would be taking the state, wrapping it around, and going back. And so clearly, because of the topology of the system, you cannot contract that green line and make it equivalent to the red line. So in principle, there are actually like as many different topological states here as there are integers. Yeah, in practice, there are actually only two. But yeah, so going back to that parameterization I cooked up earlier of like b dot tau, where these b's have some relationship to h over j cos k, blah blah blah. I don't really care. Just b dot tau. That's nicer. First thing I'm going to do, rotate the basis again, so that now. So okay, sorry, I do actually care about the coefficients. So the thing that's worth noting is that because of the sign k here and here, there is always a point in k space that's on the z-axis. So if you think about like what phi does, when phi equals 0, you have a rotation like that, or possibly a rotation like this, depending on how big h is. Whereas if you have a different phi, you sort of rotate the azimuth, but you don't change the fact that you're going through the z-axis at exactly 2 points. So what I want to do in spin space is sort of introduce some like SO3 rotation, so that no matter what the values of like kappa, h, and j no matter what these guys are up to, the path as like k goes from 0 to 2 pi always just like circles the z-axis. So boom. The next thing that is up, yeah. So what we could, so the idea that we have, right, is to try and like calculate some property of the system that will tell you whether or not that U1 bundle is doing anything interesting, and the relevant quantity here is the Berry curvature. So yeah, using polar coordinates here for this path. So yeah, this path might do this, or it might do this. We don't know yet. So, but I'm just gonna, yeah, write b is like b cos theta, b sine theta 0. Then so b and theta are k dependent, to be clear. So then the Hamiltonian matrix, sorry, so this like effective Hamiltonian h is b of k times 0 e to the I theta e to the minus I theta 0. This is very nice because the eigenvectors are very easy to calculate. They are plus or minus 1 e to the I theta. Bloody minus signs. So yeah, those are V plus or minus, and the corresponding energies are plus or minus B. Now the Berry curvature, which I'm just sort of pulling out of nowhere, because yeah, everyone in the call has seen it before, but of course, if you're interested in it, there is like a relatively easy to follow Wikipedia article on it. And it has this form. So writing that explicitly, the psi plus or minuses are the V plus or minuses. So I times the broad psi plus minus is plus minus 1 e to the minus I theta. The complex conjugates come from turning the ket into a bra, times grad k, which is just 0 I e to the I theta times d theta dk, which is actually straight derivatives because theta only depends on k. And so you just get minus d theta dk. That's all there is. So crucially, the Berry phase, gamma k, which is the integral over the full like closed path. Yeah, the Berry phase. I'm out of symbols. So the Berry phase is the closed looped integral of the Berry connection, ak dk, which is integral d theta. That is gorgeously simple. So in the xy plane now, because the motion is clearly planar, we have two clearly different cases. We have some sort of a path that encloses the origin, where integral d theta is 2 pi. And we have well, sorry, actually, it's a bit more complicated than that, because if the path sort of wraps around and goes around the origin more than once, we imagine that if it can somehow like go out of, if it can somehow avoid intersecting itself, I'm not sure how it could do that. In principle, you could get 2 pi n based on the winding number of the path. But for now, let's just say, does it go around the origin or not? Because there's only one kind of fermion in the system, it turns out that's the only situation. We have one situation where it goes around the origin and one situation where it misses it, or integral d theta equals 0. And then there's the critical value where it goes through the origin, where it's undefined. The reason for that being that when at that point, when the effective magnetic field is 0, these two energy values become degenerate. And so the whole sort of formalism around the Berry curvature breaks down. So going back to the original sort of parameterization of phase space, the idea in this 3D space is like whether or not sort of the plane, clearly regardless of the phase phi, you can find a plane in which the motion all occurs. And within that plane, the question is, does the parameterized magnetic field go around the origin or does it miss the origin? And so the critical point at which the transition happens is when this thing becomes 0. So i.e. when h over j equals plus or minus 1. So the idea is like, as you turn up the magnetic field, you go from h equals 0, which is the Ising regime, up to like the strong field limit, which you'd expect to be like a sigma x eigenstate, like they're all aligned magnetic field. But then at h equals j, you have a topological phase transition, where the topological invariant, there's a topological invariant of the system that actually changes. Now that's a huge result in physics. If you had thought of this in like the 90s, you would have won a Nobel Prize, but unfortunately we were only born in the 90s. So I guess the remarks I wanted to conclude with, right, were about, first of all, like, what does this mean for a real system? Well, there's two parts to it. First of all, what does it mean for a real system? I'm a bit uneasy, right, about this step here. We defined like these HKs on a discrete set of Ks and said, okay, as n goes to infinity, it's the same as being continuous. But of course, topologically, Z is disconnected. like even though this is like very sorry,
topologically, I think Z doesn't make sense to me. Like topologically, it should be like Q mod Z, I feel.
why Q mod Z?
Like because like it feels like it should be like discrete, but like and still connected together. Like we're filling in like the nth roots of unity, right? Actually, that might even be a more accurate. It's like
Yeah,
it's like L points arranged evenly spaced on a circle, right? So
yeah. So sorry.
the limit
So yeah, you're right.
As a topological space, the limit should be like still getting connected there. So it makes sense that the completion would be a circle.
So I guess the question is like, why is it okay? So we do have like an HK for every rational number between on an interval, but I'm not entirely certain. Yeah, so like presumably there's a physical argument to say that like irrational k's are in some way sense unimportant or unphysical, but I don't necessarily know what have a clear idea of why that is.
Well, you could just like mathematically, you could just define it like through density on the irrational case. It's like, yeah, decimal approximate it and then do stuff.
Oh yeah. Well, I mean, that is reassuring, but also, of course, the other thing is real crystals are finite. Real crystals are finite, and they're also not tori. They have open boundary conditions. So yeah, if you care to check the PDF, there is actually an explicit solution for the case of open boundary conditions as well. And the weird thing that you find, right, is, where did I put my, oh, there it is. Yeah, the weird thing that you put, right, so to explain what's happening, this is H over J, and this is the spectrum. So these E mu's, each one of these is a different like excitation of the vacuum, and the vacuum is down here. The weird thing is this red line, which correspond to zero energy modes. So in the weak H limit, there are exactly two zero energy, sorry, there are exactly two zero energy Majorana fermions. Or like you can change the basis and think of this as one zero energy complex fermion. But then above the critical field, you end up with the polarized state where all of the moments point in the direction of the magnetic field, and the system no longer has a zero energy excitation. Like the nomenclature for this would be like the system acquires a gap. So yeah, it turns out to be a very deep connection between whether or not there is a the non-zeroness of the winding number, and the presence of gapless fermions. The presence of gapless modes in the system. So this is true of the Kitaev model, and it's true of most of all known models in topological physics. And kind of something I did want to get to the bottom to at the end, at some bottom of at some point, because this isn't something I've studied in depth, is why exactly that is. But it's, yeah, but sorry, going back to sort of, countability theoretic concerns. With finite n, topologically it is like Z mod n, which is quite disconnected in a mathematical sense. So I guess the point is, in a physical system, you can make an argument from, say, decoherence, or rather by reinterpreting the sort of mathematics up to this point as the response of a system to an external stimuli, that like modes that sort of sneak through the gap between modes, are kind of need to have like, sorry, as n becomes bigger, those modes would need to have an increasingly sort of short wavelength. So you would be getting into the regime of like higher energy physics. And I guess the point is all of this physics only ever claims to work at low temperature and low energy. So that's sort of the only argument that comes to mind of like why we don't really care about, yeah, stuff sneaking through the gap. But yeah, sorry, that's pretty much all I've got for you today. Were there any points that you wanted to talk about more, or would you like me to let you get back to your lives?
Oh, I'm relatively satisfied.
Yeah.
Yeah, I'm satisfied. I mean, I
Cool.
don't really understand. It's like, I'd say it's a bit too early in the morning for a universal property, but I don't think there's ever a time where I see universal property and understand what's going on at all. Please don't try to explain it to me right now. I'm so brain dead.
I don't.
Yeah.
I'm not sure if this is a universal property or not, to be honest.
Or I see one of these commutative diagrams, sorry, and I understand what's going on. Like you drew that and you lost me for about 10 minutes, and then you drew the one at the end and then lost me until you started talking about the berry phase again.
That one's really just like,
not right now. Sorry, I'm very brain dead.
Somewhat, yeah. So actually going just momentarily, and this is going to be a half-formed thought, so it's not going to be particularly formed. Going back to the bundle.
Oh yeah.
Because the game plan with all of these things, like the game, like because effectively we're sort of forming a homotopy between like that space and like I think like the fact that there's a winding number, like you've sort of got like a direct product which sort of gives you the phase. Well, like sorry, gives you the sort of homotopy between that and like Z, right?
Yeah, I think
like
so.
I guess like the point would be that the point would be that the reason why we care about this and the sort of, you know, so like I guess like the one thing I haven't really connected would be like the sort of connection between why we care about this in a sort of like nifty bundle sense, and then connecting that to a specific homotopy. Like that sort of discrete, like that explicit 1-2, I guess.
Oh yeah.
It sort of seems like you introduced it. I mean, no, and this is just like in a general sense. I just don't understand that.
Oh yeah, no.
Because it sort of seems like it was sort of introduced, and then we just sort of went straight to like churn stuff.
No, that's a. I guess that is a good point. The reason that I did bother to introduce this is the question of like what does A mean?
Yeah, sure.
So like we can write it down, but the fact that we can write down like a number, the fact that we can write down some sort of, I guess you would call it a functional on the set of all like state vectors, in no way guarantees that that number is meaningful. Right, like we can, it's perfectly fine to like define the berry phase, but I guess the point of the sort of bundle argument is that, I mean, like I just mentioned this because I kind of wanted to say what I was actually doing, but what A actually means is that if you look, so yeah, going back to the bundle, imagine that we have like a sphere and we like label each point on, a circle, and we label each point with like a phase and so on. What A is a connection, which means that it tells you how to transport this phase from one point to another. And the reason that this is like physically significant, as far as I understand it, is that sorry. Yeah, as far as I understand it, it means that that topological invariant should be in some sense robust to like perturbations to the Hamiltonian.
Oh
So,
yeah, definitely.
So well, yeah, I'm not entirely sure. I fully understand this, to be honest, but yeah. So like rather than taking the perspective of like doing explicit by hand Fourier transforms, it's probably more helpful to look at it from in like a random matrix theory sense. And so if you looked at, say, the Ising model with disorder, where like the only thing that changes is that you have a bond dependent J. If you have like a bond dependent Ji, and you imagine like introducing some sort of small fluctuation, the idea is that inside, so we solve this at a particularly easy to solve point where all of the J's are homogeneous. But now in the more difficult to visualize like larger space, I'd argue that it's still possible to make an argument like this, but now there's we would expect like, yeah, maybe the position in K space gets like deformed slightly, and or like maybe the phases. I guess the main point is the main thing that this would do, right? If you treated like these, if you treat the disorder, say, perturbatively, what would happen is that you would. What would happen is that the K space path would remain exactly the same, but there would be some delta E. There would be like, yeah, some change in the energies that would change how the phases fluctuate as you're transported around the K loop. The point of having a topological invariant is saying that because those changes in energy have to be local, you can't like go to a different phase unless you introduce such radical disorder that you have changed the topology of the winding number.
I guess like my question would be like, are we defining are we sort of like saying that direct product that we sort of get when we sort of define our like we sort of do our bundle thing and then we like define a function like, well, sort of like, yeah, function that gives us like we have our sort of like function that maps between the direct product, and like what basically is the point that we like specifically get our sort of equivalence classes that sort of all have this same like what you're saying, right? These sort of equivalence classes that all have the same topological invariant that remain like this sort of property that's sort of protected against disorder, right? Like, are we mapping that to Z? Like, is that are we mapping? Is
that sorry. No, I might be wrong here, but I think Z is like several know what this is called, but it's like either the homology group or something along those lines.
Yeah. Okay. Yeah. Sure.
But
homotopy group.
It's also yeah, homotopy. Yeah, I guess I'm just like there's just a sort of that connection between the introducing the bundle and then like connecting that to the homotopy group. I'm sort of unsure about is basically what I'm asking. I'm saying.
Oh right. So like
confused by like that connection.
Oh right. Like yeah. Well, I mean, I guess the point is all manifolds have a homotopy group, and that homotopy group is topologically doesn't change with continuous deformations of the Hamiltonian. So I guess the point is the Berry phase is like sort of a way of writing down. Sorry, that's an explicit like topological invariant you can calculate using coordinates, but it's not the same thing as the homotopy group in general. sorry, like that. Yeah, like the homotopy group is like a more complicated object, I'm pretty sure.
Yeah, like I say homotopy group, but we mean like the first one, which is like the space of like loops in a space, like modulo with like concatenation as an operation and like modulo homotopy. So like if you can like deform one loop into another, they're the same.
Right.
What's kind of bugging me is like you say, what really are the fibers? What's actually the bundle? Like what are the fibers?
Oh,
like
the
base space is like S1 because it's
I'm pretty sure the fibers are U1.
no, but like what, like that's what they look like locally. But like what's like the actual, like what's the bundle? Actually, like what's the plan?
Oh, right. Oh yeah. So yeah, the bundle is actually saying that like if you just like take a k space point associated with that, there is a Hamiltonian.
Okay.
And that Hamiltonian will have 4 eigenvectors. Yeah, sorry. So each HK like acts on a 4D space, but 2 of those eigenvectors are always 0, and in fact, those correspond to the ones from like the other sector. Like, yeah, I didn't really address the fact that we split the Hamiltonian into odd and even sectors, but like back when I wrote down the Hamiltonian in like coordinates. Where was it?
Like
here.
There was only a 2x2 matrix.
The only non-zero block is 2x2. And like there are for each like 4D space, there are only 2 non-trivial eigenvalues. And these 2 trivial ones correspond to like these 2 like missing eigenvalues are restored by considering like the other sector of Hamiltonians. So in other words, like H odd only has like 4 to the L over, has like formally 4 to the L over 2 eigenvalues, but of those, exactly half of them are 0. So you end up with like 4 to the L over 2, but it's actually like 4 over 2 to the L over 2, which is like 2 to the L over 2. And for H even, it's the same. So you put them together and you get back the original dimensionality. But sorry, I digress. The point is like just sort of abstractly, each k space point has associated with it. Dealing with the full degeneracy of everything. Like each k space point, morally speaking, should have like is associated with an operator HK, which acts on like say C2. So that gives you 2 eigenvectors, V plus or minus. But the point is those eigenvectors after normalization. Sorry, let me rephrase it. The fibers are C. The fibers are C modulo normalization. Because the fibers like correspond to like the prefactor of the prefactors of those eigenvectors. Yeah, so like modulo normalization. Yeah, sorry, it's like C except for 0, which is I think. Sorry, is that the right word? Homotopy equivalent to U1.
Is there any reason? Yeah, it is homotopy equivalent to U1, but like, okay. It is homotopy equivalent to U1, but like saying that about the like ignoring the fibers, like only taking homotopy class for the fibers feels wrong to me, because like we're only taking the Is that actually right? Yeah, like that would be like saying that all like vector bundles are just the same thing as like saying the fibers of all vector bundles are a point because it's a contractible space. Like that feels like you're probably going to be ignoring a lot of structure. Like, is there any reason why you should quotient like by the norm of the
Yeah. Well, I mean, like I guess like arguably it's sort of baked into. Yeah, like the fact that states are normalizable is like an axiom of quantum mechanics. So yeah, I mean, like morally speaking, for something to be a physical state, it has to be normalized. But I guess like I'd also say we're not dealing with all of C. It's like C except for 0, because like the 0 eigenvector doesn't count as an eigenvector.
Yeah. Could we also like think of the like vector bundles spanned by these states and then work with that instead?
Possibly. I haven't seen it formulated that way.
It's probably easier to say.
But well, yeah, I guess the kind of issue with like dealing with the span of both eigenvectors is that you have to somehow keep track of not letting them mix. Because yeah, sort of the theorem underlying the Berry phase and like the Berry connection derivation is the one about like the adiabatic theorem. Which is to say that if you have like a slowly varying time-dependent Hamiltonian, then like the state will remain in an eigenstate of then the difference between like the true eigenstate and like a time you have a time-dependent Hamiltonian. It's following the Schrodinger equation. The adiabatic theorem says that the difference between like the true state and like the naively time evolved state goes like 1 over the time, i.e. like as the variation becomes like becomes arbitrarily slow, the difference between the true time evolution and like the like fixed time and the naive time evolution becomes 0. So yeah, because what we're doing here is like transport around the Berry phase, transport through all of K space. What we're kind of doing is applying an exponentially slow momentum translation operator, which actually corresponds to like moving the system very, very slowly to the right. But yeah, sorry. Like a fundamental thing in the derivation of Berry phase was this particular theorem. The sort of everyday reality that things tend to stay in eigenstates of their Hamiltonians. And in fact, like, and this is especially true in the presence of things like disorder and decoherence.
Hmm.
Yeah. I don't know. I should probably read Bernavig.
Benevic's a pretty fun time, just broadly.
Or possibly Nakahara.
Oh, I've just brought out. I've just brought out.
Oh, you
Nakahara.
whipped it out.
Oh,
Whipped it out. Yeah, no, I've been whipping out Nakahara quite a bit over the last week.
Ugh.
Oh, we love Nakahara, but we also hate it.
I've sort of like I'm warming. I'm warming.
All right, I might stop the
Okay.
recording.
Anyway, yeah, I'll have to.
Yeah.
Yeah, I will have to probably